Today I'm going to be showing you exactly how NMR can be used to study sodium-ion cathodes and what kind of information we can obtain using, in particular, paramagnetic NMR. We're going to look a little bit at the background of some paramagnetic NMR before actually going into examining some real spectra and identifying what kind of information we can get out of it. So before we begin with the NMR part, let's just briefly introduce sodium-ion batteries and exactly why we're looking at them. So I'm sure, as many of you are aware, there have been recent advances in the efficiency and the power of renewable energy sources, but those renewables are spatially and temporally dependent. So we need a way of being able to store that electricity during an off-peak period in demand and then release it during a peak period in demand. And one solution to this is, as I'm demonstrating here, to use batteries. And lithium-ion batteries are possibly the most famous and the most commercially successful of all the rechargeable batteries, the things that charge your devices, laptops, tablets, etc. One of the major issues, though, with lithium, there's always got to be an issue somewhere, but one of the major issues is that they're not very recyclable and they're quite expensive, which perhaps means that lithium-ion are less than ideal if we're after something which can be applied to a grid scale kind of technology. So one alternative to lithium-ion is to use sodium-ion batteries. These are ideal for grid-scale storage because sodium has such an incredibly low cost because of its high abundance. So it's ideal for scaling up to be used on the grid. And in sodium-ion batteries, what we're trying to optimize are sort of two parameters, really. It's the capacity of the material. So this is sort of how much energy you can get out, and also the lifetime of the battery. So how many times you can cycle it over and over and over again. And it turns out that really the bottleneck to both of these things is the cathode material. And we're going to be looking at that in just a little bit more detail. Before we do, just a very brief recap of how sodium-ion batteries work. So we're going to start on the left-hand side here. So the cathode is synthesized with a whole bunch of sodium already sat inside it, the anode with no sodium in it. And during charge, what happens is the sodium ions deintercalate from the cathode, diffuse through the electrolyte, and they reach the anode. And at the same time, an electron is given to the external circuit. And then the discharge is just the reverse. All the sodium's on the anode. It travels through over the electrolyte to the cathode, and electrons go through the circuit again. So let's just look in more detail at the cathode, because that's the material I said, one, I'm going to focus on, and two is also the thing that limits the capacity. So layered sodium-ion battery cathodes are probably the most commercially successful of all of the cathodes that are actually out there. And this is simply because they offer relatively good mobility of the sodium ions because of these sort of two-dimensional planes. And the entire structure of this material is essentially where you have these transition metal oxygen octahedra. They're all edge sharing, and you end up with these nice layers. And then between those layers, we have these galleries of sodium ions. And those sodium ions can, as I say, move very, very quickly throughout the material. The transition metals are simply there just to act as a source or drain of electrons. So during charge and discharge, that's where the electrons sort of shuttle in and out from. Now, one of the things I mentioned is that these are the materials which limit the capacity, and this is mostly because of the degradation. It's the phase changes which take place. It's the gradual losses in capacity due to sort of irreversible phase changes. So let's very, very briefly recap some of those phase transformations. There's sort of two different types. There's one which is layer slippage. And in essence, what happens in layer slippage is you start out with a certain stacking of your transition metal layers. And then when you desodiate, you end up with essentially areas where you have no sodium left in, funnily enough. And this, in the sort of P2 materials, this is P where you have sodiums which are prismatically coordinated, hence the P. The oxygen ions end up being eclipsed, which means there's a large amount of electrostatic repulsion in those centers. So what happens is the whole system goes, okay, I'm going to try and slip so that I can now minimize that repulsion, and I end up in a staggered conformation. And this minimizes the energy of the system. So this is sort of a layer slippage type of transformation. The other type of transformation is subtly more, sort of more nuanced, which is sodium vacancy ordering. And this essentially arises from typically charge ordering in the transition metal layer, or it's just a certain sodium content. And the sodium ions form these nice pretty patterns that we can all sort of gawp at. And these phase transformations can generally lead to degradation because you end up with, say, only a partially reversible transformation. So, you get 98% changeover per cycle, which then over time obviously just eats away at how much is actually active material is actually left over. So lots of effort has gone into trying to understand these phase transformations and trying to study them. So examples of this include X-ray diffraction, X-ray absorption spectroscopy, and of course NMR. And this is the thing we're going to be focusing on today. So the material I'm going to be looking at today is NMMO. It's this magnesium doped sodium manganese oxide. I affectionately refer to it as NMMO, so just bear that in mind throughout the talk. And essentially the structure is, again, these prismatically coordinated sodiums. And what we have an approximately honeycomb ordered transition metal lattice. So the magnesiums and the manganeses are approximately honeycomb ordered. We wouldn't expect it to be necessarily exact because we haven't got a perfect 1:2 ratio here, but it's near enough. So what exactly do we want to try and get out of these NMR studies? Well, I think the first thing is fairly obvious. We want to characterize the pristine material. One of the things we might want to address is to what extent are the magnesiums and the manganese actually, ordered in this honeycomb style? And then there's a sort of a consequent effect is how ordered are those sodium centers? Because if there's ordering in the transition metal layer, there's almost certainly going to be ordering in the sodium layer. Can we see that? And then lastly, in the last few minutes, I'll go through the evolution of the overall structure during cycling, focusing particularly on the chemical structural information and also the electronic structural information that you can obtain from NMR. And obviously, throughout today's talk, I'm going to be using sodium NMR, magnesium NMR, and oxygen NMR. Which one is your favorite? Then do let me know at the end. But if you don't have a favorite, then I'll start crying. Okay, so let's get on to methodology and exactly what we're looking at today. So in paramagnetic NMR, the dominant interaction, the overwhelmingly dominant interaction is the hyperfine interaction. This is something that's been covered in these seminars before, but just very, very briefly, it's the interaction between the time average net unpaired electron spin in a material and the nearby nuclear spins. And it sort of has two components to it. There's a through bond component known as Fermi contact, which is typically due to delocalization of electrons or polarization of paired electrons. And we also have this dipolar interaction, which is a through space type of interaction. And both of these interactions result in the same effect, which is a fluctuating magnetic field at the nucleus. And you end up with an enhanced relaxation, so short T1s, short T2s, and generally large magnitude shifts. By that, I mean a short T1 would be a few milliseconds or shorter, a short T2 is a few hundred microseconds or shorter. Large shifts, usually several hundred, if not several thousand ppm. So let's just look in detail, firstly, at the Fermi contact interaction. And I'm going to frighten everybody by putting a whole bunch of equations on the slide. But for those of you who are, aren't really that interested in the maths behind it, essentially the take-home point on this slide is that the Fermi contact shift is directly proportional to the amount of unpaired electron density that you have at the nuclear position. So whatever the unpaired electron density is that interacts with the nucleus, this is how much of a shift you end up with. So the more you have, essentially the larger the magnitude of the shift that you will end up having. The other thing that we can also note is that from these equations, this is just a property of a wave function, which means it's just calculable by hybrid DFT calculations. And this is something that Clare's group specializes in quite a lot. And then the last thing we can also note from these equations is that this Fermi contact shift, this is the parameter that we're interested in, has a Curie-Weiss-like dependence, which means it depends on the magnetic properties of the system. So if we examine that in a little bit more detail, where I've just sort of rewritten this equation in a Curie-Weiss-like way, so where this alpha parameter is essentially all those constants, and of course this spin density at the nuclear position, divided by this Curie-Weiss parameter, and this gives us these temperature-dependent shifts. And in general, the Fermi contact shifts that we see are much, much, much bigger than the chemical diamagnetic shifts you would commonly see. So unfortunately, it's not as simple as you can go on Google and you can search for a certain moiety or you can search for a certain functional group. You have to unfortunately sort of go away and either think about it or calculate it. And this is something, again, Clare's group specializes in. And one of the things that has actually come out quite some time ago now, actually, is this idea of bond pathway analysis. So this is where you can break down a Fermi contact interaction into a sum of paths, so that a sum of contributions. Say, if you're after the shift of the sodium, then you can say, okay, the manganese that's nearest has a shift of X ppm on it, and the next nearest manganese has a shift of Y ppm, and you can just add those up, and you end up with the overall shift. And the sign and the magnitude of each of those paths depends on the extent of orbital overlap. So I'm just showing a few here. If you're interested, we can chat more about it, but that's just a very, very brief overview of it. The model I'm using throughout all of this talk is going to be this system here. So this is a model system of the true system. So this is where we have all manganese 4+ rather than being mixed manganese 3 and mixed manganese 4. And I'm also assuming that all of the magnesiums and the manganeses are in honeycomb ordered arrangement. You may be asking yourself why I'm doing that, because that's technically biasing my results already. But actually, what we can do with this idea of breaking down bond pathways is, if you calculate for just a few representative systems, such as this honeycomb system, you can then obtain a single bond pathway, which then means you can actually iterate through any conformation, any sort of arrangement of the ions. So as I say, what we're trying to do is to basically calculate the amount of spin density of the nucleus. The other thing we'll obviously need is the experimental parameter, which, there we go, just measured it. So the value that we ended up with is approximately -10 Kelvin, and also the effective magnetic moment is 3.8 Bohr magnetons. The last little bit of exactly how we go about calculating these things and assigning these things, and this is where I think it gets the most elegant, is the obtaining the bond pathways step. So essentially the way that we typically do this is, if you imagine we wanted to calculate the shift of this magnesium sitting in the center of these manganeses, what we would start off by doing is calculating the shift where all of these manganeses have the same orientation of spins. They're ferromagnetically aligned. And our assumption is that basically the spin density will just be additive and they will all have the shifts of the same sign. So we just add them up and that gives us the overall ferromagnetic shift. And this is regardless of what the true magnetic state of the material is. Then what we do in a second calculation is we go, okay, let's flip one of these spins and then recalculate the shift. And what we can then end up with is just a very nice, simple sort of set of simultaneous equations where we can then extract these individual bond pathways and we can generate, for example, the delta 1 here. And this also assumes that, generally these paths are non-interacting, which is often true. And we also typically run these calculations at 2 levels. You'll see them sort of dotted throughout the talk, 20% Hartree-Fock and 35% Hartree-Fock. This is just an empirical thing. It was just found that these values seem to match best to the experiments. So this is something that is a standardized thing that has been used many, many times over. So that's sort of the Fermi contact side of things. The other component of the hyperfine interaction that I mentioned is the dipolar hyperfine. And this is a through space interactions. This is where you have a nucleus separated, an unpaired electron separated from a nucleus by a certain distance. And the strength of this interaction is inversely proportional to that distance, which means in our material, it's going to be strongest for oxygen, then for magnesium, and then weakest for sodium. And essentially the take-home point here is that the result of this interaction gives you a very broad sideband manifold. So it means that it stretches, in the case of sodium, for a few hundred ppm, magnesium and oxygen typically a few thousand ppm, as you will see a little bit later. That presents us with a very slight problem because typically the kind of pulses that we apply in paramagnetic NMR are relatively short, so we can only excite a certain width of the spectrum. We can excite a decent width, but not necessarily all of it. So how do we go about doing that? Well, the answer is VOX. So this is variable offset cumulative spectroscopy. It's a very, very simple procedure. Essentially, we acquire one spectrum at a certain receiver offset frequency. We change that receiver offset frequency. We record another spectrum. We change the receiver offset. We record another spectrum. And we keep on repeating until we think we have excited the entire spectrum. Essentially, what you're after in VOX is, if your first and last slices are just noise and everything else is signal, you've done a decent job. Essentially, the step size that you're after is just basically the inverse of the pulse length, approximately. And to get the overall spectrum, all you have to do is just sum up all of the slices. And this is regularly required for paramagnetic 17 oxygen, and I have also used it for magnesium, as you will see later. So summary so far, hyperfine has 2 components, as we already know. Fermi contact, which is this through bond interaction, dipolar through space. we can calculate certain quantities. This is the Fermi contact shift, and we can break that down into bond pathways. Using those bond pathways, we can then basically generate a new set of local environments, fit those to the spectrum, see how they compare, go back, change them, fit, and repeat. And then this gives us information about what the local environments are and how they're changing over time. Okay, so now time to actually show you some results. We're actually going to start rather curiously with 17 oxygen and 25 magnesium NMR, which is slightly more esoteric than sodium NMR, but it's a slightly easier way of presenting the results, and it's also just I think it's a nicer example to start with. Plus, everyone loves 17 oxygen. So, okay, so the 17 oxygen NMR spectrum is shown here for the pristine material, and what you can see is it spans a very, very broad region, at least 20,000 ppm, if not very slightly more. And the isotropic resonance is the one slap bang in the middle. This was identified by PJ Matpars, which is in the inset here. And you can already see there's sort of a few peaks within this central peak. And we can probably model that using at least 2 or 3 peaks. And the other thing to notice is that this isotropic resonance is clustered around about 2,500 ppm, which is consistent with what Euan, a former PhD student in Clare's group, saw for another manganese 4+ system where he did 17 oxygen NMR, and he also saw 2,500 ppm. So we know we're in the right ballpark. We don't know if we're in the right state, but we know we're in the right in a ballpark, which is good. Okay, so let's actually just sort of go about then fitting it. This is probably the best fit you could get with the fewest number of components. So we have 3 different components here, each with subtly different shifts, but all around about 2,500 ppm. Why do we get those subtle differences? Well, to look at that, we basically have to look at the bond pathways. And what we can see here is that we have a spread of values of the bond pathways, and these depend primarily on the manganese-oxygen distance, but also on the manganese-oxygen-manganese angles. So if you get a subtle variation in those lengths or those angles, then you end up with a subtle change in the bond pathway, and therefore you end up with a very subtly different environment. But I think the take-home point is, by combining these together appropriately, we can basically recreate these environments. And the way we can recreate them is just by saying that we have 2 manganese 4+ and 1 magnesium, and this generates the observed spectrum. All other combinations tend to give you a poorer fit to the spectrum. So that's sort of the 17 oxygen NMR, which gives us some quite useful, quite interesting information. Magnesium NMR is the next one I wanted to go through. So magnesium NMR, again, I have to acquire via Vox. And magnesium NMR, for those of you who are not familiar, is quite a challenging type of NMR to do. Magnesium is inherently not very receptive, has a very low Lama frequency, is very quadrupolar, and relatively low abundance. So there's a series of problems with magnesium. But our group has had some success in the past by using certain techniques. So for example, Jay here used RAPT to increase the amount of signal he managed to get. I wasn't able to use RAPT, it didn't actually work out for me, but that's by the by. So this was the sort of thing I was hoping to see. This is what it felt like I was trying to see and trying to collect, and then this is what I actually ended up collecting. So the magnesium NMR, as you can see, is relatively broad. Again, it's at least 10,000 ppm wide, so at least 5,000 ppm wide, not 10,000, at least 5,000 ppm wide. And this is acquired under 12.5 kilohertz magic angle spinning. These 2 peaks here are just background. This is confirmed from an empty stator. The other thing that I also did was to then go away and have a look to see if spinning was actually making any difference, because I couldn't really see any spinning sidebands in this. You can't really see a sideband manifold, and as it turns out, it doesn't really make much of a difference at all. The only difference here is a scaling, which is just due to the amount of mass that I had in my rotor. So this, as you can see, gives you a decent amount of information, but going about fitting this immediately, like we did with the oxygen, isn't really a smart move, because the resonance position could be anywhere within a few thousand ppm. So let's go away and look at the bond pathways first. And these are the calculated bond pathways. So a single manganese 4+ has an influence on the magnesium of around about 1700 to 1950 ppm. Again, this range is just given by previous success in the group where we've looked at a range of hybrids. And if we sum that, so we multiply it by 6 to account for the 6 manganese 4+, we can then end up with the total shift. And if we go away and we do some fitting, again, this is just the static spectrum. If we do some fitting, we can see we get 2 sites out. One of which, this site 1, actually matches quite nicely to the observed, so to the predicted, the calculated site. So this is just using the average values. So this matches relatively well. This span is slightly off, but this is the best fit I've managed to get so far. I do apologize that it's not any better, but there we go. This second site it had me stumped for a little while until I sort of realized that my material was not an ideal material. It's not the same as the model, and that actually this is just magnesium bound to 5 manganese 4 pluses and then a manganese 3 plus. And that manganese 3 plus is then giving us this different shift. Okay, so what exactly do we know so far? We know that from 17 oxygen, we can see oxygens are bound to 2 manganese 4 pluses, and we get a small distribution in the bond angles and the lengths, which is just likely, different local environments of the oxygen just due to different bonding, different strains, all those sorts of things. And then from the magnesium NMR, we can end up with the information that magnesium is almost always surrounded by manganese, and this sort of indicates that there's honeycomb order present. I couldn't identify any other clear resonances, so it's a fairly safe bet to say that magnesium is only really surrounded by manganese. This is a relatively good point to stop and ask for questions if you want to, or I can just keep going.
Let's give it, I don't know, a minute or so. If anyone has a question, they can start typing it out. In the meantime, I had a couple of questions. So does the oxygen result here also tell you it's honeycomb because you only have 2 manganeses?
Exactly. Yes, exactly. It does at least seem to suggest that. Yeah. Okay.
And can you put any sort of limit on how much non-honeycomb you have in this? Can you sort of?
Not. I can't quantify it from this. No, unfortunately not.
Okay.
I have tried to do like T2 weighted integrals, but no, it didn't.
I guess quantitativity is hard in paramagnetic NMR. Yeah. Presumably this is oxygen enriched. How do you go about doing that? Enriched,
yes, this is so this is just then heated in a 1702 atmosphere. It's just annealed at the same temperature at the final firing temperature of the pristine material.
And is it sort of is there a high enough oxygen conductivity that you're sort of enriching the whole material, or is it going to be more surface weighted, or any idea about that?
I think it's going to be slightly more surface weighted. One of the things that you can see is this diamagnetic resonance, which is quite strong here, and this is just essentially from the surface sort of crud on the material. I guess it's sort of the sodium carbonate and hydroxides and so on. I think that it is at least low bulk because it seems to indicate, just based on sort of doing SEM and so on, that it seems to be consistent that it's all the way through, or at least most of the way through. So yeah.
We have a question from Aditya Rao, who asks, what sort of time scale did the 25 magnesium NMR take?
Good question. That single spectrum, so the box, each slice of the box was 4 hours, and then it was summed over 20 of them, so it was just over a couple of days to get this whole spectrum.
Okay.
Decent amount of time.
Decent amount of times. Okay, I think I'm going to save the second question for the end because it's a more general question about batteries, but we'll come back to that one. Yep. So as I don't have any other questions for now, by all means, everyone can keep adding their questions over the second half of the talk, and then we'll have a full question session at the end. Take it away.
Thank you very much. Okay, so now that we know about the 17 oxygen, the 25 magnesium of the pristine material, the next point is obviously to go to sodium. So this is the sodium NMR spectrum. I think it's quite a pretty spectrum. It's one of my favorite looking spectra that I have. And what you can see is the isotropic resonance sitting at just over 1400 ppm. Again, this was just isolated by a PJ MapPass experiment. And now it's sort of a question of going away and being able to assign each of these resonances to a particular sodium environment. Before we do that, it's worthwhile just noting there are 2 types of sodium environments. That doesn't mean there are only two environments, it's just 2 possible types. One is called P2B, where we have phase sharing sites between the sodium prisms and the transition metal octahedra. One is called P2D, where we have an edge sharing site between the transition metals and this sodium prism. And if we go away and we do a bond pathway calculation, just as we've done before, we end up with these sets of values, which again, if you sort of look it up in terms of, think about it in terms of good enough Kanamori rules, it makes sense. So if we then go away and we go and sum up the bond pathways, we can end up getting each of the shifts. Now, to sort of tag on to one of the questions that was asked about in terms of the distribution and how much is honeycomb versus how much is non-honeycomb, what I wanted to do was to go away and have a look. Does a random distribution of the manganeses and the magnesiums, does that fit to my overall spectrum? If I just allow it to be anywhere, so that would just mean the bond pathways, you just sum up however the distribution happens to be. And this is what you end up with. And these are all isotropic resonances. None of these are spinning sidebands. They may look like it, but they're all isotropic. And essentially what this tells you is most of this doesn't really fit at all. The only ones that fit are these ones just clustered just below 1500. And if you actually look those up, those are all honeycomb-based sites. So all of these pathways are pathways which indicate a honeycomb local environment. So if we sort of zoom in on that region a little bit more and then overlay the observed spectrum, this is what we see. So we actually see the honeycomb simulated doesn't quite match all of the observed resonances. Considering that the oxygen and the magnesium were fairly well predicted, this does a much poorer job. And considering we know that this sort of technique, this technique of using hybrid DFT does allow us to assign these sorts of spectra, it's a little bit curious. So you may be wondering how on earth this arises and why this happens. And actually you may have already sort of guessed why it might happen based on the title of my talk. It's because of sodium-ion hopping on the NMR timescale. And this is sodium-ion hopping has actually been seen many times before. Some people comment on it, some people don't, but one of the very first studies to actually look at it was from Raphael, a former PhD student of Clare's, where she looked at this sodium-ion cathode material. And she noticed that by changing the MAS speed, you essentially end up changing the temperature. And this sort of has two effects. By both changing the MAS speed and the temperature, MAS no longer can suppress those anisotropic interactions. So if sodium hopping and anisotropic interactions are on the same time scale, then typically it then starts to cause broadening effects. And also you've got the effect of sodium-ion hopping as well, and that causing changes in the line shape. One of the questions you may be asking is, why does sodium-ion hopping actually change the line shape? And this is something I want to go through now because it's not necessarily completely obvious. So let's just take, for example, the idea of having two environments. So one which is called A and one which is called B, and they have distinct chemical shifts, delta A and delta B. Now, if they have distinct chemical shifts, that means they have unique Balmer frequencies, and therefore relative to the bulk nuclear magnetization of the sample, they will have a different relative phase. So that means that when you then do your Hahn-Echo experiment, which is sort of the pulse sequences shown down here, you can essentially imagine that A and B will have two different angles on these little arrows in C here. So there will be two different arrows for A and B. Now, if you have no hopping, then essentially they all just get refocused at D, and then at E you can then just acquire, and it's happy days. If you have hopping present, this can cause a sudden change in the phase because it will start off pointing somewhere over here, and then suddenly it will have to go and point off somewhere over here instead. So there's a sudden change in the phase of that nuclear spin. And this essentially results in encouraging transverse dephasing. And the rate of hopping essentially affects how much of that dephasing occurs, and therefore it affects your T2. It affects the width of your spectrum and the intensity of the spectrum as well, essentially. So if we look at this in more detail in terms of varying the exchange constant, if we start out with the scenario where we just have these two sites and hopping is incredibly slow, or alternatively it's just not really happening, then what we would see is sort of what we would normally expect, two different peaks in our NMR spectrum, just because we have two different local environments. As we then start to speed up the exchange process, the dephasing becomes quite effective because there's enough time for the hopping process that essentially sodium spends enough time in between these two resonances that a phase difference can build up. It dephases a lot faster, and you see a much broader resonance. You see a much shorter T2 for these sorts of spectra. And then as you then increase it even further, then you end up in the fast hopping regime, and you would then end up basically at a position where your shift is given just by the thermodynamic average of the two shifts you started with, the delta A and the delta B that we started with. So the main question I wanted to ask myself is this what I'm seeing in my NMR data? Is this why the shifts that I've calculated don't quite match up? And the answer seems to be yes. So this is a whole bunch of VT NMR data that I've acquired. I've got stacks and stacks more, but this is the stuff that I wanted to show to everyone today. And I'm just going to walk you through it. So there are really sort of 5 qualitative things that I'd like everybody to take away from this set of data here. First 2 are that you can see sort of general sharpening of the resonances. They become less broad and they become more distinct as you go higher and higher in temperature. And you also see a decrease in the isotropic shift. And this is just because you have greater thermal fluctuations in the time averaged electron spin moments. There's less spin density transferred to the nucleus. It just comes from the Curie-Weiss law, and we end up with a smaller shift. The third thing is that we actually have an intensity swap over. What do I mean by that? Well, if we look at some of these higher temperature spectra, you can sort of see the 3 resonances we saw earlier. We see the central resonance, and we see 2 shoulders. And as we go down in temperature, this central resonance becomes less and less intense until at some point it swaps over with the low frequency resonance. And the low frequency actually then becomes the most intense. So there's some sort of a changeover happening here. An additional thing to notice is that this third shoulder peak actually appears this third shoulder peak appears only at relatively high temperatures. And then the very last thing is that we actually see a rather strange variation in the intensity profile, which is that it decreases and then it comes back and it increases again, which is quite unusual. And this is something which occurs regardless of the MAS speed, just in case you were curious. Okay, so analyzing and simulating all of this data, how can we go about actually understanding what is occurring? The place really to start is to look at the block equations, which describe how the transverse magnetization that I mentioned earlier varies as a function of time after you have applied your pulse. So these are the standard block equations that I'm sure many of you are familiar with. So it just describes essentially how the magnetization changes as a function of time, and we can solve those fairly straightforwardly. And this is just essentially written in a sort of a tensor form just to make life slightly more. And then if we then modify these equations so that we account for a change in the number of the sites, so essentially we account for the change in the concentration at site A and at site B, what we end up with are a set of fairly straightforward rate equations. But we can then add this rate equation in here into our original block equation to end up with the Bloch-McConnell equation, which describes how the transverse magnetization changes as a function of time in the presence of chemical exchange. And essentially, this is the basis of this simulation script that I've written, which then can basically go away and predict variable temperature NMR spectra for you. Before we get into actually showing some of those simulations, the one thing I wanted to come back to is the 2 different sites, because we've got to consider what sites we're actually exchanging between in this Bloch-McConnell. And the sites we're exchanging between are a P2B and a P2D. We can't ever exchange between any other type of sites. We can't go P2B to P2B or P2D to P2D. We can only go this way around because this is how the neighbors work. Okay, so what kinds of environments might we expect in this ideal honeycomb model? Well, the P2D is always going to have the same shift. It's always going to be at the same resonant frequency because the bond pathways are exactly the same. We always have the same number of nearest and next nearest manganese and magnesium neighbors. So we don't need to worry too much about those. The P2Bs do change because we can change which ions are phase sharing and which are edge sharing. And this is essentially what we see. We can see one where we have no manganese 4 pluses, one where we have 2 manganese 4 pluses, and one which is sort of like a stacking fault one where we have only 1 manganese 4 plus sharing phases. And one of the things you can notice is that the P2D is always at a higher resonant frequency than the observed shift, and the P2B is always at a lower observed shift than the observed frequency. which means in theory, if we were to do sort of just a simple dynamic average model, any of these pairs could actually make the spectrum fit. So you'd have to go through many simulations, as it turns out, a few thousand simulations, to actually go through and identify which ones work best. But it turns out that this was the best simulation I could get. And this was the one, this is the only one actually that faithfully reproduces the data as I observed it. So this is essentially me playing around with some of the energy barriers and some of the hopping rates at which the sodium ions are hopping in the material. And if we then actually go away and assign it and we look at which sites these actually correspond to, this is what we end up with. So this is now the final spectral assignment. However many slides after I originally showed you that, this is what the spectra actually can be assigned to. So this is the high frequency corresponds to sodium going between a P2D and between a P2B with only magnesium nearest neighbors. The central one is the P2D to a P2B with only manganese 4+ nearest neighbors. And then this one is the stacking faulted hopping regime. And we can then actually go even further, and because, as I mentioned a second ago, you can have a look and extract the sodium ion hopping rates. You can actually go away and you can extract the rate at which sodium is hopping on the NMR timescale, and you can then plot it in a sort of Arrhenius type of way. And you can kind of see it's basically a straight line all the way up until about 320 Kelvin, and then you see a sudden drop in all of the rates, and then it comes back again, which indicates some sort of a new regime of motion. So then it sort of begs the question, okay, does this actually make any sense, or is this just maths just sort of, you know, doing what it normally does and just fitting something randomly, but not necessarily meaning anything? And actually it does mean something, it does fit in with other stuff. So from a whole bunch of neutron and X-ray diffraction that I have done, what you can see is the sodium ions are actually ordered in what's known as a long zigzag, an LZZ type of structure, where we have these easy free-going sodium ion chains, which are very mobile. And then we have these little islands of sodiums, which are sort of trapped in the middle and just sort of, you know, hop forwards and backwards slightly, but don't really go anywhere. And at a certain temperature, essentially what happens is these ones in the center, these island ones, get in the way of the long zigzag ones, which then causes the decrease in intensity that we saw at high temperatures. So in other words, this central resonance corresponds to these long zigzag ones because these are the fastest moving ones, and this low frequency one corresponds to these island ones here. And remember, this low frequency one corresponds to the stacking faulted one. And this is also consistent with results that I've seen in MD as well. Okay, so what have we learned from the sodium NMR? We know that the spectrum is poorly described by just a static model, so we need to account for sodium motion, and that long zigzag ordering is consistent with NMR simulations that we have. One other thing that I should also note, if you are going to do as much VT-NMR as I have done, one thing I will warn you is that Topspin does occasionally decide to make some comments on your social life, or at least I think it does, because it told me that apparently I have insufficient chilling. Anyway, but that's sort of by the by. How do the spectra change as you go through and cycle the material? Well, this is what the electrochemical profile of this material looks like. So this is just the first charge-discharge cycle. So charge is the first curve, so the blue and the red, and then discharge is the green. Don't worry too much about the colors. This is just to describe the different regimes, the different types of phases that are present. We don't need to worry about that for now. We don't really have enough time to go through it. But anyway, so what do we see as we go through and cycle the material in the sodium NMR? Well, as we go through and cycle, we can actually see a few alarming things. The first, not alarming, but noticeable things. The first noticeable thing is at this point C1, where we've only removed a tiny amount of sodium relative to the pristine material. So there should be plenty left over. We see hardly any signal. And actually, if we do VT-NMR on this sample, we see a sharpening of that resonance as we go to higher and higher temperatures. So this low intensity resonance simply arises from the fact that we've actually got slow sodium ion motion. And again, this composition corresponds to an ordered sodium ion phase. This is why it's so low in intensity, because sodium ion hopping is so slow. The other thing we can notice is we then go on to the discharge. The resonances on discharge are all very broad and low in intensity. And this suggests that, again, sodium ion motion is quite slow. But there shouldn't be any ordering at these points. Having done a whole bunch of diffraction and all sorts of other techniques, there shouldn't be any ordering at this point. So it sort of begs the question, why is it so slow here? And the answer to that is magnesium migration. So one of the things that occurs in this material is at high states of charge, high voltages, we see magnesium migrating from the octahedral positions in the transition metal layer down into the vacant sodium layers. And then those magnesium, so this is the 5000 ppm resonance we see here, and then it moves back again on discharge, and we see a resonance coming back at around about 12,000 ppm, but it's much broader, it's much lower in intensity, and this indicates that not necessarily all of the magnesium has actually returned to the ideal octahedral positions. So there's still some sitting in the sodium layer, and again, this is consistent with diffraction work that I've done, and this is probably why it's so low in intensity and why we've got such a slow motion. Last couple of minutes, then I promise I'll shut up. We can actually have a look at this material at the end of charge, this migrated material, and we can identify two local oxygen environments. And therefore this gives us a sort of a foot in the door for doing more oxygen NMR. And the two oxygen environments I'm sort of highlighting here, one of which appears to be quite covalent according to the amount of unpaired electron density that we have on it, which is this one here, it's bound to magnesium. The other one actually has unpaired electron density basically sat on it, but it seems to be strongly delocalized with the manganeses. So this indicates this is probably how the charge is being compensated. This is how the material is being oxidized. Rather than oxidizing the manganese even more, we've actually got some sort of delocalized oxidation state. And if we then sort of go even further and we do more enriched 17O NMR, and we look at the cathodes as we go through and cycle them, what we can see is the resonances start off relatively sharp, and then as we generate some of these highly oxidized species, we end up with rapid relaxation and a very, very broad resonance. So again, this is consistent with that charge compensation mechanism we saw. So I'm sure you'll be pleased to hear I'm going to stop talking now. Things I really want you to take home from this talk. I hope that I've shown you that paramagnetic NMR is genuinely an invaluable technique for studying the chemical and electronic structure of sodium-ion battery cathodes and lithium-ion battery cathodes. One of the things that we can do that's particularly powerful is you can calculate spectral parameters, fit them, compare them to models, and go back, and you can then analyze local environments very, very easily. And the last thing is, it genuinely reveals lots of information about local environments, about dynamics, and about electronic structure. With that, there's a few people I just want to thank. Phil and Mike for looking after me day to day, Jay and Euan for sort of assistance with calculations, the entire Grey group for just making the place a lovely place to work, and Guido for assistance with some of the variable temperature NMR experiments, and Claire, obviously, for just looking after me for the last few years, and everyone here for coming along. Thank you very much.
Hey, thank you very much. That was a really interesting talk, and it's really impressive how it actually makes a coherent story, which is it's easier to do the NMR than to make it into a story in the end. So to give people a chance to keep adding their questions in the Q&A box, we have a first question from Torsten Gutmann, who asks, how large are the quadrupolar interactions for sodium in the different environments in your materials, and do you have to consider second order quadrupolar broadening?
So that's a very good question. The quadrupolar interactions for sodium are actually relatively small, particularly compared to the hyperfine. What I mean by relatively small is we only really see a second order quadrupolar shift of 2 ppm or so. So it makes very little difference compared to a line width of 50 or more ppm. So I don't actually consider the second order quadrupolar interactions in the simulations. I've also acquired sort of the VT data at different fields just to try and see if you can see a change in the spectrum, and there's no real change in those at all. So there's no significant quadrupolar interaction.
Okay. And is that also the case for the magnesium and the oxygen?
Yes, it is. Yeah.
Okay. So talking of oxygen and magnesium, Aditya asks, is there any hope of doing operando experiments with oxygen and magnesium?
Oh, I would love to. I think practically that would be quite challenging, simply because you need such a you need generally fast spinning speed, especially for oxygen, because otherwise you just end up with something that's broad and featureless and you just can't see anything. So unless there's a way of doing fast NAS operando, it's going to be quite challenging.
What about the sodium? Is there any chance there?
I think that you could see something, but again, I think there's been work from our group before on looking at sort of NMCs, another one of these famous cathode materials, and doing lithium NMR, and you just sort of see something broad, and it moves a little bit, and then it moves back a little bit, so you can't see the local environments as clearly. So you could get some information, but not as much as you might like.
Okay, thanks. We have a question, and I'm going to mispronounce your name, so apologies for this. Konrad Schuska, who says, beautiful work, Euan. Manganese-containing materials often show severe dissolution in contact with the electrolyte. Do you see that in any of your electrochemistry experiments? And if so, how do you expect the structure to change?
Very, very good question. I don't actually see any dissolution, thankfully. I've done a whole bunch of studies of the electrolyte and looking at EPR of the electrolyte to try and identify like manganese hyperfine that you commonly see from dissolved manganese 2+ in the electrolyte, because it's typically 2+, which goes into the electrolyte, but you can't really see anything. You would expect the structure to change, but sodium is very, very different to lithium. In lithium, if you sort of have dissolution or a loss of transition metals, you sort of end up with the structure condensing into a spinel or a rock salt. You don't see that in sodium because there's no driving force to form those phases. So I think that's one of the things that sort of limits it from doing that.
Okay, sticking on electrolytes, what is the influence of the electrolyte if you're trying to improve the energy density of a battery final system? And is there any hope for solid state electrolytes in sodium-ion batteries?
Very good question. I think there are people doing work on solid state electrolytes for sodium ion. Sodium ion seems to be, you can get quite variable results with different electrolyte systems. The reasons for which to be honest, I don't fully understand. I would imagine a large amount of that is the development of the CEI and how the CEI is sort of able to sort of this cathode interface that forms on the very surface once you start cycling. And I would imagine that sort of the composition of that will change according to your electrolyte and how well it fits in with the overall lattice, lattice strain and so on. It's a good question, but I'm sorry I can't answer any further than that.
Okay, another question from a teacher who had a question about what field strength to use. What's the trade-off between high field, where you potentially get better shift resolution, versus low field, where your spinning speed sort of counts more? So how did you pick that?
So it's a good question. The honest answer is I picked it by sort of doing lots of variable field experiments and just using lots of time on different magnets and seeing what I saw. One of the issues you have is that because these materials are paramagnetic, the higher field you go to, the faster the relaxations, the broader the resonances become. So you may get better resolution, but actually they all condense into each other, so your resolution gets worse. So you've sort of got to find a nice balance between the two. In my case, I got lucky enough that using the 11.7 and the 16.4 Tesla actually still gave me relatively good resolution. But in some systems, you lose a lot of resolution. If you go to lower fields, you again also lose a lot of resolution. So sitting in the middle generally works quite well.
Okay, that makes sense. So a question from Chloe, who says, thanks, Euan, very exciting results. The honeycomb ordering seems to make sense from an electrostatic perspective. Is it possible to get, for instance, 50-50 magnesium manganese to allow for other potentially frustrated orderings?
Also, very nice question. So this is something that's been studied a few times, is trying to sort of stuff more magnesium into the material. Unfortunately, the compound that I was looking at is the most magnesium you can get into this material. If you go any further, you just end up with just impurity phases. And also it becomes a much worse battery material because you just have fewer transition metals. It would be nice just to do that from a simple magnetism perspective, but unfortunately I look at batteries.
Okay. Another question from a teacher who wants to know how you did the low temperature spinning without crashing your rotors. What's your trick?
Being really careful. paranoia is a wonderful thing sometimes. I think one of the things that I just ended up doing was you just sort of cool down by like 5 degrees, and then you cool down by another 5 degrees, and you just gradually cool more and more and more until you get to your temperature. If you do it all in one hit, you can end up basically just causing a massive instability and it just crashes. That's how I ended up doing it.
Okay, and these were cooling with liquid nitrogen, the VT gas, or
yeah, it was liquid nitrogen with the VT gas. Yeah.
Okay. Okay. Well, I had a question about your hopping simulations, which fit very well, which is nice to see. So, if I understood correctly, the assumption was you're only hopping back and forth between, so always the same of the second site.
Yep.
Especially, and so you then kind of justified that because your islands can only hop back and forth, but your zigzags could do longer range hopping, and so do you not have to account for potentially hopping from one site and then back to a different type of site? Could you expand on that?
So that is it's a good question. I wasn't massively clear. The nice part about the honeycomb ordering is that all of those P2D sites are locally identical. The number of nearest and next nearest neighbors are the same, so the shift should be exactly the same. So
those different regions are actually in different parts of the sample.
Yeah.
On what sort of length scale is that?
What kind of length scale is that? That's a good question. It's typically it's only a few angstroms. So I mean, if you sort of hop 3 times, it's be about 5-7 angstroms, somewhere between those.
Okay. So any further questions? Type them out quickly. Oh no, sorry, I found a new one. Nahum Enkubari, again, apologies if I've mispronounced your name, asks, thanks for the nice presentation. Have you studied the effect of doping on hopping?
Oh, you mean like compared to the pristine material? I haven't. That was an earlier study that was actually done, and they essentially just saw that your hopping becomes faster and faster as you add more and more magnesium, because essentially in the just the NaMnO2 type material, you end up with a lot of Yarn-Teller distorted manganese 3 pluses, which generate these very, very strongly ordered array of sodium ions and vacancies. So you end up in a scenario where hopping is incredibly slow.